Good morning everyone. The title of my presentation is shown in the current slide. The presentation program is as follows. 1. Introduction, the problem description. 2. Modal approach to acoustic field description. Assumption, mathematical model, modal analysis and acoustics, modal amplitudes. 3. Experiment, the chosen object with measurement point and acoustic source place. 4. Wavelet analysis as the tool, time frequency domain. 5. Results and conclusions. This paper deals with the problem of reduction of the acoustic resonances, which may occur when a source is placed inside the domain. This kind of problem appears in room acoustics. When same places or locations inside the enclosure are preferable to avoid the situation, the speech became unintelligible and people not loud and clear because of unwanted example. In case of devices, this location makes their work louder and more oppressive. According to that, the research aimed at creating the best acoustic properties of the room is the most common problem in this area of interest. This work deals with the problem of identification of chosen acoustic field values. On the one hand, a source placed inside the domain in the specific location may generate slower values of acoustic pressure than sources, which occupy other places. On the other hand, those areas are strongly dependent on the domain shape. It is confirmed theoretically, which is presented in this presentation section: modal approach to acoustic field description, assumption, mathematical model. Next, in the section experiment, the chosen object with measurement point and acoustic source place. The specific experiment is described, which is conducted in order to get actual acoustic field values in the case of specific sound source and measurement points and example object. In last section, wavelet analysis as the tool, time frequency domain. The wavelet analysis is introduced in order to identify specific feature of measured signals. The presentation will be summarized with the conclusions. An acoustic field in an enclosure is a specific case of acoustic wave propagation, where the sound source inside generates an acoustic signal, which is usually partly absorbed and partly reflected by boundaries. If source is permanently active, the acoustic energy absorbed on boundaries is equalized in the short term by the energy from the source, and after a transient period, the steady-state acoustic field dominates in an enclosure. In this case, in order to describe the acoustic field distribution inside a room, the modal approach can be applied, under several restrictions, conditions and assumptions. One of them is a low-frequency range of signals generated by a source, which is limited by Schroeder frequency. This kind of signal and low range of frequency guarantees that sparsely distributed acoustic modes of the enclosure are excited. The desirable enclosure property, which gives an uncoupling modes possibility application, is high enough boundaries impedance. This work based on the modal approach assumption that an acoustic field distribution inside enclosure is dependent on its normal modes, eigenfunctions, which are solution of the Helmholtz equation in the case of a domain with perfectly rigid walls, i.e. Neumann's boundary condition equals to 0. In other words, the eigenvalue problem has to be solved in order to get eigenfunctions, Greek capital letter psi m r, determined in all enclosure points with coordinates r, x, y, z in enclosure and eigenfrequencies, small letter omega m. Simultaneously to apply Greek capital letter psi m r in modal expansion, which could be in the form of following sum shown in the gray rectangular shape, in manuscript equation 1. The orthogonality and normalization of eigenfunctions are required. In the case considered in this work, i.e. low frequencies and narrow band of excitation, infinite sum can be reduced to finite number n of factors in the sum. The first factor in modal expansion, the time components Pn, describe acoustic pressure variation in time, i.e. an increasing sound when a source starts and a decreasing sound when a source becomes mute. In the case the field in a steady-state condition, Pn represents magnitude of acoustic pressure in particular point of the domain. If the sum describes the acoustic field inside the room with a source, it satisfies the linear, inhomogeneous wave equation in the specific boundary conditions. most often determined by the acoustic impedance. Introducing modal expansion in a classical, well-known wave equation, in manuscript equation 2. Qn is source function, in manuscript the second case of equation 5. Rn is damping coefficient, in manuscript the first case of equation 5. Generally, Rn coefficient represents damping in the system caused by the boundary impedance, and Qn is a source component in equation 2. The source component in each equation is an integral of specific eigenfunction multiplied by a source magnitude in points where the source is located. Outside of the source location, an integral vanished. Moreover, if a eigenfunction, Greek capital letter psi, and in the source location get values close to 0, whole source component in 5 and consequently related time component Pn t in 2 get minimal absolute values. Simultaneously, bearing in mind that solution of wave equation is assumed in the form of sum 1, which contains time components related to all eigenfunctions, the problem of acoustic field pressure values reduction is focused on searching of minimum of products, the source magnitude and particular point and eigenfunctions values in this point, i.e. the source location. Therefore, without regard for damping in the acoustic system, impedance boundary condition and strength of a source, there is a space configuration and area region inside, which guarantee minimal values of acoustic pressure, whereas others induce the responses. In order to identify the required parameters, i.e. resonance frequencies and damping of an acoustic system, the object shown in Figure 1 is investigated. The volume 5 is about 4.5 m3. The real acoustic impedance characterizes the boundaries in the actual object. Applying finite element method, FEM, the eigenfrequencies and eigenfunctions, Greek capital letter psi m, r, can be identified to solve numerically previously shown equations. It was done to compare the following experiment. In the case of an acoustic source, the low frequency is enough to apply first 500 eigenfrequencies. The experiment configuration is presented in Figure 1. The location M1 and 4 represents microphone locations, whereas LS is loudspeaker location. In all measurements M1 M4, the loudspeaker generated acoustic impulse. Hence, the sound source frequency spectrum is chosen properly introducing impulse signal in actual experiment. Here, the Gaussian impulse in a low frequency range is applied. These signals are described in the time g, t, and frequency h, f domain by the following formulas. Where f0 equals 200 Hz and s equals 1 millisecond. The f0 equals 200 Hz provides not sharp but specific frequency distributions, the frequency band of the impulse. On the other hand, the parameter f0 determines the concentration of the frequency components in this specific frequency 200 Hz neighborhood. The measurements for M1 and 4 microphone positions are presented in Figure 2. The red arrow indicates the impulse directly recorded without any acoustic wave reflection and its length is an acoustic pressure amplitude. The results shown in the figure give information in time domain. Without additional analysis it is only seen the attenuation of the acoustic signal caused by an acoustic wave reflection and the damping of medium i.e. air. The reflected wave resonances are seen in form of peaks appearing in measurements. In the case of Figure 2, A and D, their amplitudes in initial phase take values on a comparable level of impulse. In other cases, the resonances are on lower level. It means the system damping is higher. The strength of each peak received is different and clearly depends on the microphone and the source place. The peaks are directly correlated with eigenfrequencies. It is not possible noticed in time domain but theoretically proof. Here conducting the experiment, the acoustic pressure in points M1, M4 is obtained. In the case of the examined object, where boundaries are characterized by relatively high values of acoustic impedance, the eigenfrequencies should be possible to identify applying particular analysis. This feature is particularly useful in dynamic systems analysis, where strong variations in time appear. Further, It is expected that the frequency analysis gives the information which frequencies in recorded signal are well received, on the contrary to the others, which are strongly damped or vanished. In this work, the specific wavelet approach is chosen. The following wavelet features were used with some limitations. The wavelets, compared to windowed FFT and classical FT Fourier transform, leading to the flexible analysis in frequency time domain. The wavelet transform WT can be treated as a kind of digital zoom, allowing to look inside the analyzed signal as deeply as we want, not only on frequency but in time direction as well. Here, one should be aware that in this focused process, that Heisenberg's uncertainty principle comes into force. The wavelets are functions f(t) with specific properties ordered in their importance. The wavelet family represents the basis, which has a Fourier transform qf
omega.
The wavelet's functions oscillates. The values of wavelets tends to 0 and minus and plus infinity of time domain, and the wavelet's function in their Fourier transform contains main amount of energy in its center. It shows following integrals. The signals M1 and M4 analyzed in this paper have been transformed by using the Morlet wavelet FMT with different parameters, seen on figures. Mother wavelet, normalized to maximal value 1, analytically is defined in following analytical form 1. The wavelet transform W(A)(B) of an arbitrary signal is calculating using wavelet function, shifted with B in time and scaling within frequency domains according with following correlation formula 2. In analysis, the continuous wavelet transform is introduced, what means that scaling and translation parameters A, B vary continuously over real values with restriction, A is positive. Eventually, the wavelet transform W(A)(B) of each signals is obtained applying Morlet wavelet with proper parameter P and shown in figure. The set of coefficients W(A)(B) obtained as the result of transformation is related via parameters A to so-called pseudo-frequencies and via parameters B to time domain. The legend on the right-hand side of figures indicates values of wavelets coefficients W(A)(B), which represents the analyzed signal and shifted wavelet correlation level. The wavelet transform obtained using Morlet wavelet with parameter P equals 24 of signals measured in location A, M1, B, M2, C, M3 and D, M4. Red dashed lines indicate the object A eigenfrequencies calculated solving the eigenvalue problem using FEM. After a series of testing simulations, this type of wavelet was chosen as the appropriate one for analyzing the measured signals, in order to analyze the most wanted features in time-frequency domain. But wavelet approach gives the most powerful feature allowing mention above focus opportunity. Increasing values of parameter P1 can deeply look inside the time domain, otherwise a frequency domain is particularly investigated. This is presented in figure. On figure, wavelet transform obtained using Morlet wavelet with parameter P equals 24 of signals measured in location A, M1, B, M2, C, M3 and D, M4. Here, again red dashed lines indicate the object A eigenfrequencies calculated solving the eigenvalue problem using FEM. Here, time focus. The wavelet transform obtained using Morlet wavelet with parameter P equals 28 of signals measured in location A, M1, B, M2, C, M3 and D, M4. Again, red dashed lines indicate the object A eigenfrequencies calculated solving the eigenvalue problem using FEM. The figures show that wavelets have the possibility to recognize more detailed features of signals. The wavelet analysis can be used for the recognition of features such as A eigenfrequencies, even if they are recognized in damped acoustic system and differ from perfectly rigid system. The signals in time domain, figure 1, behaves chaotically. The significant information is spread in time domain, compared with one obtained via wavelet transform. More analysis are presented in the origin manuscript. The paper presents a multidisciplinary approach to the wave propagation in bounded space. This approach is based on follow-up analysis, theoretical description of this problem, a further examination in form of the experiment and measurements observation, finally proper analysis introduction. These analyses were conducted for signals generated and received inside closed space, the object I inside the room. The theoretical background was presented in order to point out special attributes of these signals such as frequencies components associated with the eigenfrequencies of the object and their duration. In the case of the object, eigenfunctions were identified numerically, and according to the theoretical solution, the measured signals contain specific components correlated with the eigenfunctions. The wavelet analysis allows to identify this specific time of this component's duration. That points out the system damping for particular frequencies. Thus, by using the wavelet transform, a number of physical and geometrical properties of the object is depicted, which leads to the recognition of surrounding environment with generated impulses. On the basis of the carried out experimental study, one can formulate basic guidelines for acoustic signal analysis that can be also introduced widely to room acoustics and other vibroacoustic problems. Thank you for your attention.